Good morning. We will start today. I have LNMIT class in front of me. So, any questions from last time, LNMIT? Okay, PG, PhD, CT, it's fine. There are no questions from last time. We will go on with today's class. The agenda was to find out the L, inductance per unit length of the transmission line using the Maxwell's equation that we learned. So last time what we did was the Maxwell's equations for magnetic field. We defined what is H, and we said the current carrying element, if I have a steady current I passing through a wire, Oersted discovery said that there is a magnetic field around it, and according to Biaxial's law we quantified what is the magnetic field, how much is the magnetic field. We quantified the magnitude as well as the direction of the magnetic field, and then we defined Amperes law, which simply said that the loop integral of this magnetic field H dot is nothing but the current enclosed. And we used Stokes' theorem to say that if I have an arbitrary loop, the loop integral H dot dl can be looked upon as the curls to the surface. So this is nothing but the surface integral curl of H ds, and the right side is surface integral J dot ds, because if I consider a loop, J is the current density, which is current per unit area. Total current would be the surface integral of current density. On the same side, I get curl of H minus J ds equal to 0. Now this should be true for any arbitrary surface, so we demand curl of H should be equal to J. Remember, this is for steady current. This is what we did last time. This was the point form, and this is the integral form for the Amperes law, which is again a Maxwell's equation. Now we are going to use this idea to find what is the inductance. Now we also defined B, the magnetic density, as permeability times H. Now go back to the definition of inductance. We defined inductance as flux per unit current. L was magnetic flux per unit. So if I look at, for example, we're going to take an example transmission line. You take a coaxial cable. which has, as we discussed the other day, an inner conductor of radius A and an outer conductor of radius B. Now we want to find the inductance in this region. Now what we are going to do for that is, suppose I think about this, I straighten this, I rotate this coaxial so that this is my conductor which carries, say, some current. This conductor has a non-zero radius, the radius is A. This is the outer conductor. This is the lateral section of the coaxial line. The idea is, if I use my right hand rule, I know what is the direction of magnetic field here. So if the current is propagating from bottom to top, I use my right hand rule, which means my thumb should point to the direction of the current. Then my direction of rotation of the fingers would give me the direction of magnetic field. So which means into the plane of the paper that I am writing, and in this region, so it's going in and it's coming out through this. So the magnetic field, if I look from the top, this is the inner conductor, this is the outer conductor, the magnetic field is actually curling around. The direction of the curl is decided by the direction of current here. Here I am saying the current is flowing outward, so the direction of curl is in the counterclockwise direction. If the direction of current is into the plane, then if I point the thumb into this board, then my current direction, my H direction is in the clockwise direction. Alright. Now what we want to do is the flux. Now how do I find the flux? So magnetic flux density is B. So magnetic flux should be equal to surface integral B dot ds. Because flux density is flux per unit area, so I integrate over the area, I should get the total flux. To do this, I should know what is B. But to know B, I should know what is H. So the problem reduces to finding out what is H and then find B, then find flux and then find the L. This is our algorithm. Just like how we wrote down an algorithm to find the capacitance per unit of time, where we said let's find D first, electric field, electric flux density and charge and so on. Here the first step is to find H, then use B equal to mu H to find B, then find flux with this definition of flux, magnetic flux, and then my inductance is flux per unit current. This is the plan. Now the question is, how do we find H? Now I have the current through this. I know that the H is curling around this. Alright. I straightly use the integral form of Amperes law, which says loop integral H dot dl is the current infused. Alright. If I figure out how to find this loop integral, I know how to find H. Remember the cylindrical coordinate system we did yesterday. We use the same cylindrical coordinate system because the symmetry of the problem has symmetry, so we use cylindrical coordinate system. problem has spherical symmetry, I would use spherical coordinate system. So in this coordinate system, this is my, if there's another color here, this is my dl, and h and dl, remember last time we said this is r, this is phi, and the unit, so phi is the angle made by the projection of this point on the xy plane. So dr, or sorry, dl is along the direction of a phi, so is h, because h is also curling around. So at every point in space, h takes the direction of a phi. So my h is actually h phi, a phi. And what is my dl? As I pointed out here, dl is this elemental length in the direction a phi. Now I can define that elemental length in terms of r and d phi. Let's say this angle is d phi. I can write this elemental length as r d phi in the direction a phi. Alright. So my h dot dl integral, the dot product is, both of them are in the direction a phi. So cosine of the angle between them is 1, and I want to do a complete loop integral, which means I have to traverse from this end all the way, go back to this end. Now while I am traversing around this loop, my r is not changing because I am at the same distance from the axis. My z is not changing, the height is not changing because I am looking at a loop which is at the same height. I am not looking at a tilted loop. The only variable that is changing is phi, and that phi will start from, when I start from this end, phi is 0. When I rotate and come back, my phi is 2 pi. So my phi is 0 to 2 pi h phi r d phi. That is my left hand side, and the right hand side is I. Let's say I is the current through the conductor. So at every point there is a current I in the conductor. Do this integration, you will get h phi r 2 pi is I. So my h vector is nothing but I over 2 pi r a phi. So I have used Amperes law to find out current, to find out the magnetic field due to the current carrying conductor in this coaxial cable. Now, as we said earlier, this magnetic field intensity does not depend on what is the material between the inner conductor and the outer conductor. It does not depend on the material. Whereas the flux penetration should depend on what is the nature of this material, whether it's magnetic, non-magnetic, etc. So that is flux density. We are going on to the second step now. The first step is done. That is mu times h, which is the magnetic permeability of the material. Material is non-magnetic, magnetic permeability is mu naught. So this is mu I over 2 pi r a phi. Now the next job, third job, is to find the magnetic flux. How do I do that? What I do is, I have to use B dot ds, surface integral B dot ds. B now, which is this. So now my task is to find which is that elemental surface area that I should be looking at. So again, go back to the same diagram. This is the outer conductor. This is the inner conductor which has a certain diameter. I am trying to find what is the flux that is crossing this area. You take a section of that conductor. I am worried about how much is the flux that is crossing this area. So to be able to do that, I take an element surface area ds, okay, of let us say length L, whose width is dr, because you see this is the cylindrical coordinate system. So what is my ds? Is length times dr, and what would be the direction of ds? Direction of ds is always the direction of the outward normal to the surface. And what is the outward normal now? Outward normal in this cylindrical coordinate system, the outward normal is a phi. I have drawn a lateral section, so a phi so this should be a phi. This is mu I by a phi, which is my magnetic field L dr. In fact, I can say that this is dz because I have considered an elemental area. So instead of dl, I can use dz. So this is dz ar, dz dr a phi, and then the z is running 0 to say L. I have a length L of the transmission line. Again, phi will run from, well, phi is not the variable for you is, so R has to run from, this edge is A, the other edge is B, so it has to run from A to B. That is my flux. So if I do this integration by 2 pi, dz integration will directly give me L, dr over R will give me ln of R between the limit A and B. So this is mu I L by 2 pi of D by A. Alright. So the third job is done. Now I can go back and do the fourth step, which is flux is current per, sorry, inductance is per unit current. So this would be mu L by 2 pi, and you know, for a transmission line, the transmission line parameters are defined for per unit length cases. So L per unit length would be mu over 2 pi ln of D over A, which means if I know what is the inner radius and outer radius of the transmission of the coaxial cable in this case, and if I find permeability of the material that is in between the cable, between two conducting wires, I can what is purely physical properties. So that is the beauty of it. You are able to connect the electromagnetic property with simply the physical property of the cable. So we did for the transmission line, we did capacitance, we did inductance. Now we had two other parameters, which was conductance and resistance. We had said that for ideal lines, G is 0, R is 0. But for non-ideal lines, you have a non-zero value for G and R. So as of now, we have calculated the parameters of a ideal transmission line. Yesterday we calculated what is C, today we have calculated what is L for an ideal transmission line using electromagnetic field concept using Maxwell's equations. The next job is to find R. So what we could do is today we could find the conductance also, because that needs only the knowledge of again the idea of what is potential and what is field. So this we calculated using Gauss law. This we calculated using Amperes law. So these are actually, I have chosen it in such a way that they are, examples of how you can use Gauss law and how you can use Amperes law. Now we are going to calculate this also today. So what is this conductance we are talking about? Ideally, the inner conductor and the outer conductor of a coaxial cable are supposed to be totally insulated, which means the material that you have here in between the conductors, what I am shading as green, that has to be a perfect insulator. But in a practical coaxial cable, this is not an insulator, with the result that whenever there is a current through this, there is a leakage current which flows through this insulator either from the inner conductor to outer conductor or from outer conductor, depending on which of the conductors is kept at a higher potential. So this is the leakage current, and the conductance that we are talking about, G, is that due to the leakage current. That is the conductance we are talking about. Now to find this, again I will tell you what is the algorithm. What we do is first find current density. Then find E, because electric field with J is sigma E. So if I know J, I divide it with the conductor of the material, I get the field. Once I know the field, find the potential. Once I know the potential, use the relation V equal to IR to find the resistance. Once I know the resistance, conductance is 1 over resistance. This is the algorithm I am going to use. So what is the first step? You want to find out what is the current density. Let us say because of leakage I have a current I through the dielectric material, the insulating material there. And I have already given a direction for this current. So what should be the current density? It should be the current per area in the direction AR. Question is, what area am I talking about? So what we do is, for coaxial element symmetric to the system, and the current and the area that we are talking about is that of this coaxial element inside this. So what is my area? So let us say this element is at a length r, distance r from the center, and let the length of the element be L. So my area is nothing but area of surface cylinder, because the current is passing only through the surfaces, the curved surface. There is no current through this end faces. There is no current, there is no leakage current through the end faces. So the curved area is nothing but the curved surface area, which is 2 pi r. So my J would be current divided by 2 pi r L AR. First step is done. Second step is find electric field from here. Find the electric field. Electric field is J over sigma. So this is nothing but I over 2 pi r L sigma AR. Third step is find potential. Now potential is minus integral A to B E dot dl. If I am assuming that, again as I said, this negative is indicating that work has to be done against this field, against this direction of a field to move a charge. So this is minus integral A dot B, A to B, I over 2 pi r L sigma AR dot, what is the deal that we are talking about? We are talking about the field which is in this direction. Let me draw it with another color. So my field is in this direction, and when I talk about potential, I am either moving the charge in the direction of field or opposite to the direction of field. If the charge is moving in the direction of the field, as the up, I have work done by the field. So essentially my DL, the path that I am taking is along the direction of the field. So the path that I am taking is actually dr AR. So this would be I over 2 pi L sigma R integral A to B. 2 pi L sigma ln of D over A. This is my potential. And the last step is to find out resistance, which is over I. I don't worry about the sign here. As I said, when I calculate resistance, I don't say it's negative resistance, right? I don't worry about the sign because the sign is thing, as I said, only the sign of the work which is either done by the field or against the field. So voltage by give me ln of V over A 2 pi L sigma. And conductance in that case would be 2 pi L sigma over ln V over A. And in transmission line we define these parameters per unit length. So G per unit length is equal to 2 pi sigma over ln V over A. In terms of the physical parameters of the line, we managed to define the conductance. Remember, for a pure dielectric, this sigma is close to 0. So your conductance would be always negligibly small. Intuition behind this calculation is we want to be using Ohm's law. So if you were to use, because that's the simplest way of calculating resistance. So if I want to use Ohm's law, I need potential. And if I want to know what is field. And how do I get field in this direction? What is this electric field? It is because of this current density in the region between the two conductors, which is why I started calculating current density. So that was a simple enough calculation based on the definition of field and potential to calculate the conductance of the transmission line. The last thing calculated is resistance, which is not a very straightforward thing to calculate. You think that the resistance is the simplest thing that you could calculate. But the resistance that we are talking about is the resistance of this conductor, the inner conductor, to the flow of current. And we cannot calculate that without the knowledge of electromagnetic waves. Right? So we need to get to electromagnetic waves before we could calculate what is the resistance per unit length. Because I'm going to say that these electromagnetic waves are trying to penetrate through this, the conducting wire, and the resistance offered by the wire to that is what I need to calculate. Right? So get to electromagnetic waves. Electrostatics, if I had stationary charges, it gave me the concept of electrostatics, where I am defining electric field, potential, work, and so on. If I have steady current, I get the concepts of magnetostatics, where we define H, B, and so on. Electrostatics gave us Gauss law. Magnetostatics gave us Amperes law. Now, if you have moving charges or time varying, instead of saying moving charge, in fact charge is current. So it is not correct to say moving. I should specify what kind of movement that is. If I have time varying charges, then it leads me to the concept of electromagnetic waves. So whatever Maxwell's equations with until now, it was Gauss law and Amperes law essentially, dealt with stationary charges and a steady current. Now if I have current changing as a function of time, or if I have a charge which is changing as a function, it is giving rise to current, but I have a current that is changing with respect to time, I have electromagnetic waves coming into picture. So we will take the case, one case where we talk about Faraday's law, which even in your high school you have learned that, because Faraday's law is the first instance where I am talking about something that is time varying. Otherwise, charges were stationary, current was steady, there is nothing time varying, nothing changing as a function of time. Faraday's law is the first case where I encounter when I have something changing with time. And what does Faraday's law state? If I have current conducting loop, well, I have a wire, a conducting loop, it does not carry any current, it need not carry any current as of now. It is just a loop which can potentially carry current. And let us say this is kept in some, there is some magnetic field H, corresponding to which B, corresponding to which there is a flux. Now if this flux is changing with time, if this flux changes with time, or in other words I can say the magnetic field changes with time, then there is EMF induced in the conductor. That is your Faraday's law. So if I were to state Faraday's law, it is simply this: induced EMF in a current carrying conductor is equal to minus rate of change of magnetic flux. So the idea is, when the magnetic flux changes with time, there is an EMF induced in the conductor placed in the changing flux. I mean, it obviously cannot be induced conductor which is kept somewhere else. Of course, this conductor has to be placed where there is a magnetic flux, and the magnitude of that induced EMF is negative time variation of this. It has to be negative, it can't be positive, because of the following reason. If there is an EMF, I will have induced current, right? And I know from Oersted law, Biaxial law, that induced current will produce its own magnetic flux. So you have a flux due to induced current. I originally had a flux because of some external magnetic field. Now I have a flux due to the induced current. Now this, because phi is changing, you have a VEMF, you have an H, you could have phi induced, that will add up to this induced phi, then it becomes a non-conservative system. So which is why the induced flux is in such a direction, or the EMF induced is in such a direction, the current produced will flux which will oppose the change. This is your Lenz's law. The negative sign was given by Lenz. Otherwise, it will become a cumulative, the magnetic flux will keep on increasing. So, you can't maintain conservation. Now, you know VEMF, I am just going to restate this. I am going to write down what is flux, which is B dot ds. And it is interesting to note that Faraday's law does not talk about change in B or change in area. I just need a change in flux. And the change in flux can be because my magnetic field is changing, or it could be because the area is changing. Which means, how can I think about a physical situation where mass is changing, where magnetic field is changing? Let us say this is the loop which is kept in this magnetic field, which is produced by an electromagnet. Alright. So, if I change the current in this electromagnet, I can change B. And because this B changes, I can have an EMF in this loop. That is one way of changing flux. The other way of changing flux is, my B is constant, but I change the size of the loop. I increase the size of the loop, because I shrink the loop, I expand the loop. I keep doing that by some way, physical way. Then also I can produce an induced EMF. But if we are assuming that ds, or the area of the loop, is constant, then I can write this as del B by del T dot ds. Partial derivative, because I could have B changing, or I could have B could change with time, space, etc. So, I am looking at B changing with respect to time. This is induced EMF. I know from the definition of EMF, minus E dot dl, I have put loop integral here because I am talking about the EMF induced in the complete loop, is minus missed this surface integral, so that surface integral should be . Now, I use Stokes' theorem, which says that if I keep which says that over a surface, if I keep taking the curl of the vector field, I add up all the curls, I should get, so the curl would be this. If I all these across a surface, get the loop integral. So, I can write this loop integral as integral of curl of E is surface integral del B by del T. So, well, when I write as a loop integral, I don't have to worry about the sign, because my induced EMF over the loop would be the total curl. There is no negative sign because when you are going from A to B against the field, from point A to B against the field is when you would write a negative. But in this case, you are having a loop. You are completing that integral over the loop. So you would have this. So you have this negative sign here, which would help us write del cross E plus del B by del T is 0. Now this should be true for all surfaces that you consider or any surface that you consider. So it should be independent of the surface. So del cross E equal to minus del B by del T. This is your Faraday's law. And this is the integral form of the Faraday's law. Well, this one, the integral form of this. So, to just consolidate all the Maxwell's equations we derived, first was Gauss law, which said divergence of D is rho. Of course, we wrote down what is the scalar form and the vector form for this. We wrote down point form and the integral form for this. Second, we wrote down the Amperes law, which said curl of H. That's what we use today also, right? We wrote down, we started with Amperes law, curl of H is J, the current density. The third one we are writing down is Faraday's law, says curl of E is minus del B by del T. There is a fourth one which does not have a name, which simply says divergence of magnetic field is, or divergence of H is 0. Reason being, if I can think about current carrying conductor and the magnetic field which is circulating around it, divergence would mean, what is the physical meaning of divergence? We discussed that. Suppose I have a charge rho, if I draw the electric field around it, we know that the electric field is diverging, spreading out from the charge. But if you try to take, so if I take a unit or I take a arbitrary surface around the charge, I can calculate how much is the flux density and I will get a non-zero value. Whereas if I do this for a magnetic field, similarly like this, I take a closed surface, I take some arbitrary closed surface around this and I am trying to find out how much is the flux to find what is the divergence. I will realize that on one side the magnetic field will be leaving, and from the other side the magnetic field will be entering the area that I. So the net outward flux or the net inward flux in a magnetic field is always 0. So these are your 4 Maxwell's equations. Now there is a correction that needs to be applied to this Maxwell's equation, considering the equation of continuity, so in tomorrow's class, which is probably the last class, we will do this correction to Maxwell's equation and then discuss what the boundary conditions are. I will be sending 2 more tutorials for you to work. We could, if from the students or from the participant colleges, we can extend this, get to waves, and finally talk about resistor unit length, but that would require 1 more class. As per the QEEE sessions, my session is ending on next Tuesday, so during which I will be able to bound conditions. I will do equation of continuity and modification of Amperes law and boundary conditions in the next class. If you wish me to do waves and calculating reflectance resistance per unit length, please inform, if you have an interest, please inform the QEEE team. I can do 1 more class on it. Alright, so we stop today's session and the session is now open to questions. Okay. I have a question here from PSGCT. In general, what is the relation between electric flux and electric charge? So remember our last discussion, or you can start from Gauss law itself. The differential form said this, or said is Q enclosed. In that sense, the total flux. The total and the total charge enclosed are dimensionally the same. But flux is telling you, or rather flux density is telling you how much is the flux per unit area. In that sense, they are different. Flux density, so any given surface, if I know what is the flux density, I can calculate what is the flux through any surface. I have a question from GCEEBD.
Good morning, ma'am. Good morning, ma'am.
Yeah, go on.
Ma'am, I want to ask a question. In the coaxial cable for the calculating conductance, the current is total current that is through the conductor or leakage current, or including both?
In calculating, I will repeat the question that I covered. Calculating the conductance coaxial cable, which is here. What is the current that when we say conductance, what we are talking about is the conductance of the region to okay, let me repeat. When we are calculating the conductance for a coaxial cable, what we are talking about is the conductance in the region, I don't know what happened to my figure, but anyway, the region between the two conductors. So we are talking about the current through the dielectric. So the current that I am talking about is the current through the dielectric. because I am trying to calculate the conductance of the dielectric. Does that answer your question? Okay. I have another question from PSDCT. In electric circuits, we can say that AC current is that true? Question is, isn't a vector? Well, AC current is not a vector, it is a phasor. So, it has a phase associated with it, it has an amplitude associated with it. The phase tells you, gives you more information about the voltage or current. I wouldn't actually call it vector, I would rather generalize and call it as a phasor. In transmission line, we have another question from MLVGTC. In transmission line parameter, if we already had R, why do we take G into account? So, to answer that, go back to the transmission line. Again, I repeat, what is the, so if you take a coaxial cable, inner conductor and outer conductor of a coaxial cable, the G is the conductance of the region between, in the shaded region. G is the conductance of the region or dielectric between the two conductors. R is the resistance of the line itself. R is nothing but the resistance of the line which is carrying current, whereas G is the conductance, or G is telling you how much is the leakage current. Current is expected to flow through the inner conductor, and the resistance of a current flow is R, whereas current is not a dielectric, and the conductance of the dielectric is hope that answers. Thank you to the team. Whether you want one more class than what we had planned. If you do not inform, I assume that you want only one more class, and that we will do on Tuesday. Thank you.